All right, guys, looks like the quiz is pretty much timed out. So let's go ahead and get started with what we want to talk about today, which is ultimately valence shell electron pair repulsion theory, or VSEPR, which is just a fancy way of defining molecular geometry. Now, it's the concept that we introduced in the video for last night. And what we talked about in the video, this is really just a simple table that I pulled out of your textbook and annotated a little bit. So it's there in your textbook if you want to use it. It's actually really helpful. I'd say have it handy when you're doing homework problems and things like that, because this is how you learn the geometries. But basically, if you look at that first column there where I have parent there written, those were the situations, the 5 different situations that we talked about in the video, where basically we have bonds, okay, around the central atom, and each bond represents a pair of electrons. And what we're trying to do here is to get those electron pairs as far apart from each other in 3-dimensional space as we possibly can. And the reason for this is because those electron pairs or groups repel each other. Okay, so we're trying to minimize repulsion by getting those electron groups as far apart from each other in physical 3-dimensional space as we possibly can. Okay, so we talked about the linear, the trigonal planar, the tetrahedral, the trigonal bipyramid, and the octahedral geometries. Those were our parent geometries we introduced in the video. Now, I also mentioned to you in the video that several of these, actually 4 out of the 5 of them, have what we call subset geometries. Okay, and where the subset geometries come from is when we have a non-bonding or lone pair of electrons on the central atom, 1 or more of those. So basically what ends up happening is we have a parent geometry, but then we have a subset of the parent geometry that comes about. So take a look, for example, on the second row, where trigonal planar is your parent geometry. Notice what happens if one of those pairs of electrons is a non-bonding pair. So that's the one I kind of put the little balloon around just to emphasize it so you could see it. So ultimately what we end up doing is we kind of cover up that non-bonding pair and then look at what we've got left. And if you do that, what you'll see is that we have what would be called a bent or angular geometry, okay? Now the bond angle is still going to be around 120 degrees, which is what we would actually expect from a trigonal planar geometry. Actually here, notice that they say it's a little bit less than that. And the reason why it's less is that a non-bonding pair of electrons actually takes up more volume than a bonding pair. So it kind of has a tendency to sort of scissor that bond together a little bit closer. So that's why the bond angle is actually a little bit less than 120. Okay, but it still stems from that 120 degree bond angle that we derived last time from the trigonal planar in the video. Okay, and notice that, of course, as you get more non-bonding pairs around the central atom, you get more options or more subset geometries. So by the time you get down to octahedral, notice that you have 1, 2, 3, 4 different possible subset geometries that we can have. Okay, so we're always going to reference back to this chart here. So that's why it's kind of handy to have it around when we're talking about these things. All right, so I just took a picture of it there so you guys could see it. All right, so what I want to do now is move back into our notes and start a new set here. And we are on May 3rd, so that is 5-3 bonding notes. Okay, so what I want to cover today, of course, is going to be some actual examples of how to utilize VSEPR or molecular geometries. So what this means is that we're going to basically start with some Lewis structures, and then from those Lewis structures, we're going to dictate what the geometry ought to be. And it can either be a parent geometry or it can be a subset geometry. So let's just see where we end up with this by looking at a few examples. Okay, so the first example I want to look at is a polyatomic ion. It's NCO1-. Okay, so if we go ahead and draw a Lewis structure for it, we should be able to verify that we have 16 electrons to work with. Carbon ought to go in the middle, okay, because it's the most metallic of the atoms that I've got. Put an oxygen on one side and nitrogen on the other, and we'll start using up our 16 electrons. 1, 2, 3, 4, outer atoms next. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so there we've used all the electrons up. Look for your octets. Nitrogen's got one, oxygen's got one, carbon does not. So we're going to have to make some multiple bonds into carbon to get an octet to carbon. There's a few ways we could do it. One way is we could make 2 double bonds. So we'll just look at our options. All right, so we could do this. All right, and let's just take a look at our formal charges while we do this. Okay, so you should be able to verify the formal charges as we go. So nitrogen's going to have a formal charge of -1, carbon's going to be 0, and oxygen's going to be 0. Okay, so that doesn't look too bad. All right, now I see another way I could do this to minimize the formal charge on the nitrogen. I could actually make a triple bond between the carbon and the nitrogen. That's another option I could have. Still gets my octet to everybody that needs one. And we'll put our 1- above this just to verify that this is indeed an ion and not an atom or something with a neutral charge. So now take a look at your nitrogen. Looks like I've got a formal charge of 0 on the nitrogen, a formal charge of 0 on the carbon, and a formal charge of -1 on the oxygen. So it kind of looks like it, first glance that we're kind of splitting hairs here. And in a sense, we are. If I had to pick one of these Lewis structures as being the best for minimizing formal charge, I'd probably pick the one on the right. And the reason for that is because oxygen is a little bit more able to accommodate that formal charge of a -1 because it's a little bit less metallic. It lies a little bit more toward the right-hand side of the periodic table. But again, we're kind of splitting hairs here. Now, from the point of view of VSEPR or molecular geometry, it really doesn't matter because what we're looking at is electron groups around the central atom. Okay, and when I look at this, I've got an electron group there and I've got an electron group there. If I want to go with the other Lewis structure, here's an electron group, here's an electron group. Now, the trick is when I have multiple bonds like this, I'm just going to treat a multiple bond as a unit. It's an electron group. So a single bond is going to be the same as a double or a triple. Okay, because all those electrons are acting as a unit. Okay, so ultimately I've got 2 groups around the central atom here. So if I have 2 groups around the central atom, what's my geometry got to be? So what's my parent geometry? What do you guys think? I kind of gave you the answer by drawing it out that way. You're exactly right. It's linear. Now, do I have any subsets under linear? No, I don't. So linear is what we've got. That's the actual geometry as well. So yeah, very good, linear. So what about my bond angle? So a lot of times we're asked for bond angles here. So what does the bond angle in a linear sense have to be? Anybody remember from the video? And again, it's kind of right there in front of you. So if you're good at geometry, you can tell me what that bond angle is.
180.
You got it. Very good. Okay, so we're linear with a bond angle of 180 degrees. That's the most we can do with this. That's as far as we can go. Okay, so this is a good example of a linear molecule. Okay, so another one. Let's do another polyatomic. Let's do nitrate. NO3 1-. All right, so counting up, it looks like I'm going to have 24 electrons to work with. So again, we always start with a Lewis structure. Nitrogen's going to go in the middle. I'm going to go ahead and surround it by oxygens for my Lewis structure. Start making bonds. 1, 2, 3, 4, 5, 6 outer atoms. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so have I satisfied the octet rule? Well, I have on everybody but nitrogen. So how am I going to get an octet to nitrogen? We'll make a double bond. Doesn't matter which oxygen we do it with because they're all equivalent. So we'll do it there. All right, so that takes a 1- charge. Now, if you look at this thing, I can't start messing around with other multiple bonds because nitrogen's over in row 2, so it can't take an expanded octet. So this is the best I'm going to do. So I'm not even going to bother messing with formal charges here. All right, so count up how many electron groups you've got around the central atom. And I see 3, okay? So if I have 3 electron groups around the central atom, what's my parent geometry going to be? What did we call that when we had 3 electron groups around the central atom? In other words, let's go back to bond angles. That might help us. So if I want to make those bond angles as big as possible, what are we going to have? What are they going to be?
120.
120. Very good. All right. So in other words, I could actually draw this thing with the bond angles at 120 if I wanted to, just so you guys can see what it looks like. So it's going to look something like that. And I'll put my 1 minus up there to show that it's indeed an ion. Okay, so if you follow those bond angles all the way around, they're all 120 degrees. Okay, so what did we call that? We had a name for that. Anybody remember it?
Isn't it the trigonal planar?
Yeah, exactly. Trigonal planar. It's a triangle in a plane. Yeah, exactly. Very good. All right. So again, that's the best we're going to do there. But everybody sees how this is all working. We got to get a Lewis structure first. Then once we have a Lewis structure, we can start defining the electron units around the central atom. Then we can start getting at a geometry. All right. So let me do another one here. I want to get somewhere we got some lone pairs around the central atom. So how about this one? XeF4, that would be Xenon Tetrafluoride. Okay, so it looks like I've got a total of 36 electrons there to work with. Okay, so I'm going to have 4 times 7 is 28 coming from the fluorines and 8 more from the xenon. Okay, so the xenon's got to go in the middle. We'll surround it by fluorines. Again, this is just a Lewis structure. We're not terribly worried about geometry yet. Make some bonds. 1, 2, 3, 4, 5, 6, 7, 8 outer atoms. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, so I'm 32 out of 36. Where do the other ones go? What's our rule? Where do we have to put the other 4 electrons? They go on who? Outer space. Where are they going to go?
Xenon.
Yeah, you got it. 1, 2, 3, 4. There they go. All right, so now we're good. We've satisfied the octet rule on everybody who needs an octet. We've used up the electrons. We've put an expanded octet on xenon. Xenon can handle that because of where it is in the periodic table. Okay, so now what I'm going to do, and sometimes I'll put a little balloon around these so I don't forget about them. So sometimes I'll just do that. So let's talk about our parent geometry here. So for my parent geometry, I'm going to count up the total number of electron pairs or units around the central atom. And I see that I have 4 bonding pairs and then 2 non-bonding pairs. So that's a total of 6 pairs. Okay, so what do I call a geometry that has 6 electron units around the central atom? What is that? We had a name for that. That was called the AX6 situation, right? So what's an AX6?
Octahedral.
Octahedral, very good. But now notice that not all of the electrons are actually going to be bonding electrons. I have 2 pairs of non-bonding electrons, so I kind of have to cover them up and pretend they're not there. So let's just look at bond angles for the parent geometry. Okay, for an octahedral, remember that the bond angles are all the same, right? So essentially, you can see that if I'm looking straight up and down on this thing, I've got like a square plane with the xenon bonded out to the fluorines. So those bond angles are all going to be 90 degrees. And if I now think about it, the non-bonding pairs are kind of sticking straight up and down. So if you look at that, that's also 90 degrees. So an octahedral has bond angles of 90 degrees all the way around. But now, what about my subset? So this would be my actual geometry. So in this case, I'm going to draw it a little differently. I'm going to take the xenon here just so we can see it a little better. And I'm going to sort of flip it over. Okay, so now the square plane is going to be here in the plane of my whiteboard. Okay, so I'm going to have an F there, an F there. I'm not going to bother to put the electron pairs in. We know they're there. And then straight up and down in the y-axis, I'm going to have an electron pair there, and I'm going to have another electron pair there. Okay, so now notice this thing forms a square, doesn't it? So if I'm looking straight down on it like that, okay, what's my subset geometry called? If I kind of ignore or cover up the non-bonding pairs, the thing in the bubbles, what am I left with there? It's a square, right? And it's a square in a plane. So what would I call that? Kind of like trigonal planar, I could call this what? I would call it a square planar. And if you go back to that diagram that I gave you right at the very front end of class, you'll see that square planar is a subset of octahedral. And the bond angles are still 90 degrees. Okay, so that hasn't changed. But now my actual subset geometry, which I would call this, is different. It's a subset of the parent octahedral. Okay, so sometimes you'll see this as like an AX4E2. Sometimes you'll see it represented that way because the X are the things I'm bonded out to. So the X's represent bonding electrons and the E's represent non-bonding electrons. So it's still an AX6 subset, but it's an AX4E2. All right, so everybody see how that works more or less? And again, I needed a Lewis structure to get to that point. So let's do sulfur dioxide, SO2. All right, so SO2, what have I got there? It looks like I'm gonna have 3 times 6, 18 electrons. Okay, let's see what we got here. Sulfur goes in the middle, oxygen on either side. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so what do we do here? We need to make some double bonds, right? So probably the easiest way to do that in terms of getting everybody an octet would be to do that. All right, that's probably the simplest thing to do. All righty, so in a situation like this, what have we got? Again, it looks like it's a pretty standard situation. You can pretty much look at that one and tell what we're dealing with. What do you think the geometry ought to be? What does it look like to you guys? Oh, I figured you guys would be all ready to jump on this one, right? What's that geometry? It's not even a subset. That's an easy one.
Linear.
Yeah, it's linear. And my bond angles are going to be what, 180 degrees. Good. Okay. All right. Let's
Don't we still only
do.
have 16 electrons?
Did I not put the other ones on there? Did I do that wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, it looks like I did do that wrong. Oh, this gets a little more interesting then. Yeah, I missed it somehow. I thought I had 16. Thank you. So what would I do with that last pair of electrons to correct this? Thank you. I'm going to put an X through that because that's going to change our Lewis structure and our geometry. Where should I put that extra pair of electrons? Here's what we have, right? Okay, so there's my 16, is that right? And I needed 18. Where should that extra pair go?
On the sulfur?
On the sulfur. Very good. Yeah, that'll make things a little more interesting. Now, if we wanted to, at this point, we still have to make a double bond, don't we? Because we're still going to be deficient on the sulfur. So now I would have something that looks like this. And a pair there. All right, now put a little bunny ear around it here. All right, so that's a good one. So in this case, what's my parent geometry going to be? How many electron groups do I have around the central atom? Looks like I have 1, 2, 3. So what's my parent geometry here going to be?
Trigonal planar.
Trigonal planar, good. It's an AX3. But I also have a subset, don't I? Because one of these guys is actually going to be a non-bonding pair. Okay, so if I actually, again, drew this accordingly, here's my trigonal planar, what it ought to look like. By the way, one of the nice things about Chem 101 is if you guys have already noticed, when you put Lewis structures in Chem 101, it kind of already draws them out in the correct geometries for you, which is actually really, really nice. Okay, so if the parent is a trigonal planar and I cover up the lone pair on the sulfur, what am I left with as a geometry? What did we call that when we kind of covered that extra electron pair up?
Bent.
Bent, very good. And our bond angles are still going to be 120 degrees. Now you can make the argument that the actual bond angle here will actually be a little bit less than 120 degrees, but my theoretical bond angle is still 120. Again, the idea here is that the lone pair on the sulfur takes up a little more volume, so it kind of pushes the existing bonds a little bit together. Kind of think of it as like scissors closing up. Okay, but if you said it's going to be about 120, you're good with that. So it's a bent geometry with a bond angle of 120 degrees. Okay, so you kind of sort of see how this goes. So what I want to do now is open up some Chem 101 and get a little more practice with this. And again, feel free to access that little table that I showed you or what have you, because that will make it a little easier to pick these things out. But let's pop over to the Chem 101 and see what we got. I'm actually going to leave that open right there, and we'll just go right over to the Chem 101. Matter of fact, if you guys want, I could even project that up on my screen here. So that might help you guys. I've got 2 screens today, which is nice. So I can watch Chem 101 on one of them. And I could project something useful to you guys on the other. So let me actually pop back out to that photograph that I had for you. Let's go there, go back to my photos. And there's that nice there's that nice helpful table for you guys to use while you're grinding through this. It looks like we got, what, 4 problems here to work on. And by the way, they use some funky terminology here. They ask for electron domains sometimes. Electron domain just means parent geometry. What's the parent geometry? Anybody got any questions about these ones? Guess I'll be happy to go over any of them you want me to.
Could you do question 4?
Sure, let's have a look. Question 4 is the CHOCF. That one? Yeah, let me pop back over to my notes here. Glad to. CHOCl. All right, so let's count up our electrons. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You get 18 electrons as well. That's what I come up with. Okay, so it looks like carbon ought to go in the middle. Then we're just going to surround it by the other stuff. The hydrogen over there, oxygen over there, chlorine over there. That's everybody, right? All right, start using up electron pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I think I counted them right that time. Now remember, I can't put anything else on the hydrogen, right? Because hydrogen only takes a duet. So now we need a double bond. So the question becomes, would you rather double bond in from the oxygen or the chlorine? Which one do you think would give you a better formal charge? And you could work it out both ways if you wanted to. My gut tells me the oxygen would be the way to go. Okay, so I'd have a C, and we'll double check with formal charges when I'm done. That's a chloride. Let's check formal charges on everybody. So let's see. Chlorine looks like it ought to have a 0. Carbon should be a 0. The oxygen looks like a 0, and the hydrogen looks like a 0. So that's the way to go to minimize our formal charge. Okay, so now, how many electron units do you have around the central atom? Looks like 3 to me, right? So the way I might draw this to show the actual geometry would be this. All right, so what's that geometry look like? And it says determine the ideal bonding angles. Well, okay, let's do the ideal bonding angles since that's what it's asking for. Okay, so what do those bond angles look like? Looks like to be 120 degrees all the way around. If I wanted to define a geometry for this, it would just be a plain old trigonal planar. Hopefully that's what the answer is. I can check and see. Yep, we got the right one, and it looks like it's saying 120 degree bond angles. Yep, that looks right. That makes sense.
Yes, that makes sense.
Awesome, thank you.
I have a question. When is our final?
You know, I honestly haven't looked. Anybody got the answer to that question? Hopefully sometime during finals a week. Now, the one thing I will say about it is I think the university has dictated that all finals are supposed to be remote, so nobody needs to be on campus to take it. So you can take it wherever you're going to be. Okay. I have not looked ahead. Anybody know?
No idea.
But I promise you, I will go find that information for you. Somebody did actually send me the final exam schedule about a week ago, but I just haven't bothered to look at it yet. I work about a week out. That's about the best I do.
Okay, thank you.
No problem, but I will get to you that on that. I'll probably just send it out probably as an email, just as we wrap everything up so everybody knows exactly what to expect.
Do we have to take it on Zoom or?
I'm not going to require it. I think you're just going to have a time to come in and check in. I mean, it's basically going to be set up so that everybody does it at the same time during the time the university says it's going to be on the day and time. And I'm just going to set it out there just like a regular quiz. It's just going to be a long quiz, right? And you'll have X amount of time to do it. And that'll be that. So it'll be just like what you've been doing all along. All right, guys, any other questions? So watch the next video for Wednesday, which is, I believe, an introduction to electronegativity and bond polarity. So that's going to move us to the next step. So we're almost there, guys. We're on a sprint to the finish here. So I will see you guys on Wednesday.